Hey everyone, welcome back to Engineering Education. For this next problem, we have another RLC circuit of second order, and here we're asked to find the capacitor C such that no reactive current is taken from the source. So here we have a source of 240 volts, 60 hertz, a couple of resistors, a 7 millihenry inductor, and the capacitor that we're solving for. So as always, pause the video, give it a shot, and we'll go over the answer in a bit. So to go ahead and solve this, we need to understand a very important concept, and that concept is called resonance. And so resonance occurs when the inductive reactance of an inductor is equal to the capacitive reactance of a capacitor. So it occurs when XL is equal to XC. And when XL is equal to XC, something strange happens, and the passive elements, the inductor and the capacitor, cancel out, and for a parallel combination like the one that we have here, they become an open circuit. And essentially, the total impedance becomes purely resistive. So this would be your regular voltage divider circuit if these two were in resonance. And so when the capacitor and the inductor are in resonance, they kind of oscillate energy between each other. So the inductor gives energy to the capacitor, and at that same frequency, the capacitor absorbs that energy and then sends the energy back to the inductor absorbs it, and they kind of oscillate back and forth, sharing this energy. And essentially their net reactance is going to be zero, and the circuit becomes purely resistive. So here we're going to derive the equation for calculating the frequency at which these two components resonate at. You don't really have to do that. I'm going to do this for completeness. You can go to the FE handbook where this equation is given. But just to give you an understanding, an intuitive feel for what is really going on in the circuit, we're going to derive it. So XL is given by 2 pi FL. And we're going to set it equal to XC, which is 1 over 2 pi FC. And what we're going to do is we're going to try to isolate F, and ultimately we're going to solve for C. So we're going to multiply both sides by 1 over 2 pi L. So 1 over 2 pi L, giving us F on this side, and 1 over 4 pi squared FLC. And then we'll multiply by F on both sides, giving us F squared is equal to 1 over 4 pi squared LC. And so we can take the square root of both sides, giving us F is equal to the square root of 1 over 4 pi squared LC. And rearranging that, we can rearrange it as follows: 1 over 2 pi squared of LC. And if we multiply both of these by 2 pi, so again this is equal to F, we get the definition of omega, while these cancel out here. And so we get that omega is equal to 1 over square root of LC. And that is the exact same equation that you're going to find in the FE handbook. So here we are in the FE handbook. We have a resonance section, and the equation for resonance is given right there, 1 over the square root of LC, and that is for both series resonance and parallel resonance. So that's the equation we're going to use to solve this problem. Going back, we need to solve for C using this resonant equation. We know what omega is and we know what L is. And so when you rearrange this equation here, you get that C is equal to 1 over omega squared multiplied by 1 over L. And plugging in the values here, we get 1 over 2 pi times 60 hertz, which is our omega. We square that, and then we multiply it by 1 over 7 millihenries. When you do that, you get roughly 1 millifarad. So that is our answer, 1 millifarad. So that means that if we set this capacitor to 1 millifarad, it would become in resonance with the inductor of 7 millihenries, and they would exchange energy back and forth such that their reactive components cancel out, and we have a purely resistive circuit. And if we have a purely resistive circuit, then there is no reactive components, meaning there's no reactive current, meaning that there would be no reactive current taken from the source. So I hope you guys enjoyed this video. If you did, please leave a thumbs up. Please let me know in the comments below if there's any other videos you'd like me to post. Please subscribe if you haven't already to the channel, and share this with your friends or anyone else you might think will find this information valuable. And thank you guys for watching. I'll see you guys in the next video. Until then, enjoy engineering.